Hey guys, welcome back. We're going to do 1-4 today, which is all about inductive reasoning. And it's a pretty short lesson, hopefully. So we're just going to jump right into it. Two objectives for the lesson today. By the end of this lesson, you should be able to use inductive reasoning to identify patterns and make predictions based on data. So if you see a pattern, what do you think is going to happen next? And then the second objective is to use inductive reasoning to provide evidence that conjectures are true, or provide a counterexample to show that they're not true, to disprove them, okay? We only have 3 vocab today, and there's no theorems. So our new vocabulary is conjecture, counterexample, and inductive reasoning. So we are going to go to your terms page in your packet towards the end there, and we're going to talk about what these 3 vocabulary mean. All right, so our first term here is conjecture. So a conjecture is an unproven statement that is based on patterns or observations. So if I gave you a pattern of 1, 3, 5, 7, you would probably say that the next number in that pattern is 9. You have no way to prove that that is the next number, right? But you're making that assumption based on a pattern that you see or an observation that you see. So we're actually not going to write anything here, but just know, so a conjecture it's unproven, but it's a statement that's based off of a pattern, okay? A counterexample, an example that shows that a statement is false. So if I said something along the lines of everybody in my classroom's favorite color is blue. That's a conjecture, right? It's an unproven statement, and I'm only saying it maybe because everybody in my class is wearing blue. But then a counterexample would be somebody raises their hand and says, Miss G, my favorite color is green. So then that would be a counterexample, because then my statement of everybody in my class's favorite color is blue is no longer true, because somebody in the class has a favorite color of green. And then the last vocabulary that we have is inductive reasoning. So this is just using our mind, right? Using our super powerful brain and using any patterns or observations to make a prediction. So it's very similar to a conjecture, right? But this is the actual act of us, hey, I'm going to use this pattern, right? 1, 3, 5, 7. I'm going to use that pattern to then reason that the next number will be 9. So those are our 3 vocab that we're looking at for today. We're not actually going to write anything in, so that's exciting. Okay, so 3 terms, and then we're going to just look at today, how are we using those 3 terms to make observations and to look at some patterns within our lesson, okay? So I'm going to go back up to the lesson, and we're going to get started. Okay, here we are back at 1-4 lesson. So we're going to just start with example 1. And it just, example 1 is all about using inductive reasoning to extend a pattern. So what this means is I'm going to look at A, and I see that a pattern is happening. I have 88, 82, 76, 70, 64, etc. And it looks as though, let's pick a different color today. It looks as though I'm subtracting 6 every single time. Right? That's what the pattern is doing. So what are the next 2 terms? Well, if the pattern is continuing, then the next term would be 58, right? 64 minus 6 is 58, and then 58 minus 6 is 52. And then that pattern would continue. And that's what those ... dots mean, is that the pattern would continue. Same thing for B. Let's see if we can figure out what's happening here. Here I'm adding 2, but here I'm adding 4, and so on and so forth. So it's kind of weird. So I'm going to write down what's happening. So I'm adding 2, and I'm adding 4, and I'm adding 6, and then 15 to 23 is 8. Okay, so it looks like I'm adding by a number that's increasing by 2 every time. So then the next number I would add is 10, right? So 23 plus 10 is 33. And then I would add 12, and 33 plus 12 is 45. So you're not always adding the same number every single time. In this case, it was very helpful to me to write down what am I increasing by every single time. And then I was able to see a pattern up in there. So I want you to go ahead and try A and B and give it a shot, right? It doesn't hurt if you mess up. That's why we use pencil. So go ahead and try A and B, and then when you're ready to check your work, just hit play, and we'll have the answers up here. Okay, so for A, hopefully we saw that we were dividing by 2 every single time. And so then I got 50, and then after that is 25. For B, it's a little bit harder, right? I don't see a number that is dividing, right, or 18 to 24. I don't see what I'm necessarily adding there, because 18 to 24 is 6, but 24 plus 6 is 30, not 32, and then I have this weird 128 over 3. So it looks like very, very confusing here. So a little trick is to take your second term, which is 24, and divide it by your first term, which is 18. And I'm just going to reduce that fraction, and I see that 6 goes into both of these, so 6 goes into 24 4 times, and 6 goes into 18 3 times. So this tells me that I'm actually multiplying, 3 times. I said 3 and I wrote down 6, didn't I? So this tells me that I'm actually multiplying by 4 over 3 every single time. So then my next number in the pattern or in the sequence would be 128 over 3 times 4 over 3. Right? So every single time I multiply by 4/3. And then I multiply by 4/3, and so on and so forth. So when I multiply this out, 128 times 4 is 512. And then 9 times 9 is 3. Wow, 3 times 3 is 9. It's really ready for my nap time, I guess. 3 times 3 is 9. So that's my next number. Okay, and then all I'm going to do now is multiply by 4/3 again. So 512 over 9 times, it's like minus times 4 over 3. And 512 times 4 is 2,048 over 9 times 3 is 27, and that does not reduce. So that's the next number. And then I could keep going, right, and find the next number and the next number, but it only asked me to find 2. So all we're doing here is using inductive reasoning to figure out a pattern and then to extend that pattern by 2 more terms. For example 2, we're going to use inductive reasoning to make a conjecture. Remember, a conjecture is an unproven statement. So we're going to use inductive reasoning to see if we can come up with a rule to help us find other patterns. So let's get rid of that, and let's look at example 2 here. So example 2 says, what conjecture, so what statement can be made about the number of dots in the nth term, where n can be any number. So I want to find a pattern so that if I want to know how many dots are in the 100th term, I can figure that out. Or if I want to know how many dots are in the 50th term, I can figure that out just by plugging in the number. So that's my goal. Okay, so n, just to make a little note, n is the term number. n is the term number. Okay, so here, I just want to kind of, let's just make some observations. If my term is 1, right, n is 1, I have 2 dots. Are we okay with that? So let's just say the column is, there's 2 columns, so 1, 2, right? So 2 columns. One row. And the row is this way. Okay, so I'm just making a statement that, or I'm just like writing down what I see. I see that there's 2 columns and I see that there's 1 row. If n is 2, like it is here, there's 3 columns and 2 rows. Okay, and let's do, well, we can keep going. So if n is 3, in this case, right here, I have 4 columns. I'm going to abbreviate. And then I have 3 rows. And then if n is 4, I have 1, 2, 3, 4, 5 columns. And 1, 2, 3, 4, 4 rows. I'm just writing down an observation. That's it, right? So what I notice here is that whatever my n is, I have 1 more than that number of columns, right? Like if n is 1, I have 2 columns. If n is 2, I have 3 columns. If n is 3, I have 4 columns. So 1 more number of columns. And then whatever n is, I have that many number of rows. So let's say if n is 1, I have 2, right? So one of the number of dots, or sorry, the columns is, let's say, n plus 1. This is the columns. Right? Whatever n is plus 1 gives me the columns. And then whatever n is the row. Hopefully that makes sense here, right? So if n is 4, I have 4 plus 1 columns, so 5 columns, and 4 rows. So now all I'm going to do is I'm just going to simplify this. I'm going to distribute. Well, n times n is n squared. And n times 1 is n, so plus n. So this right here will give me the number of dots that are in each row, or in each term. So this will give me the number of dots. So if I want to know how many dots are in the 100th term, right, I can just plug in 100 and solve. If I want to know how many dots are in the 20th term, I just plug in 20 and solve. So this will give me the number of dots that are in each term. Okay. So here I want you to try this one. See if you can come up with a pattern. Really inspect it. Take some time. Pause the video. Really inspect it. Take time. See if you can come up with some sort of pattern, okay, that to help you figure out how many dots are in each term. So really, really take your time and see if you can figure it out, and hit play when you're ready. Okay, so hopefully we started figuring out kind of how many dots are in these. So in the first term there's 1, and then here there's 5, right here 9, 10, 11, here 16, 17, 18, 19. And so you could have kept going and figured out how many dots are in the 5th term. So in the fifth term, you should have 29 dots. Okay, and then in the next term after that, you should have 41 dots. So there's multiple ways you could have figured that out. So any one of the ways is fine. But part B is now asking you for the actual conjecture. What's the equation? How could I figure out how many dots are in the 100th term, right? Or 150th term or whatever. So we need to start looking at this and figuring out some sort of pattern that we see. Here I see n is 1, n is 2, right? N is 3, and n is 4. And so what I kind of noticed here is that when n is 2, I kind of have this 2 by 2 square, right? So this is like 2 times 2. Let's write it here. Right? 2 times 2. So there's 4. And then this right here is 1. And then here, this guy is 3 by 3. And then this is 2 extra at the top. And then in this square, we're kind of looking at 4 by 4, and then 3 here at the top. So what I kind of noticed is that whatever n is, right, 2 times 2, I have n times n, right? If n is 2, it's 2 times 2. If n is 3, it's 3 by 3. If n is 4, it's 4 by 4. So it's n times n. And then I also have to include this number. So now I got to figure out a pattern with this number. When n is 2, it's a 1. When n is 3, it's a 2. When n is 4, it's a 3. So I notice that it's 1 less than whatever n is. So it's n, but it's n minus 1, right? Whatever n is, if it's a 4, n is 4, it's 4 minus 1, which is 3. If n is 3, it's 3 minus 1, which is 2. So the conjecture here, well, I know that n times n is n squared. And then I can't really do anything with this n minus 1, so I can just say plus n minus 1. And that's the conjecture. That's going to be the pattern. And that'll allow me to find the number of dots in any of these terms. If I want to find the 100th term, I'm going to plug in 100 here. Okay, so that's what's going to help me find the 100th term, or the 50th term, or whatever term it is that you want to find. So if these two problems are like really confusing for you, or you need extra help, reach out to me, reach out to your teacher, and let us help you on these, okay? Because we want to make sure that you are understanding how to do these. Okay, surprise. I had to leave to go coach soccer, so I had to stop the recording, and now I'm at home. So I know that this one's a little weird, but that's okay. We're going to keep moving on in our notes. So I think we are on example 4. I actually don't remember, so if I mess that up, please just let me know. But example 4 is to, what we're looking at is to find a counterexample to show that a conjecture is false. So if I have a statement, right, a conjecture is just a statement. So if I have a statement, like I said earlier, everybody in the class, their favorite color is blue, right? That's a conjecture. And then the counterexample would be if somebody raised their hand and said, no, Miss G, my favorite color is green. So that would be a counterexample to show that it's false. And I'm just going to warn you ahead of time in case my dogs start barking or something. There's probably going to be background noise, so just work with me here. So for example 4, my conjecture is a polygon with diagonals has 2 fewer diagonals than sides. So a polygon is just a shape. Okay, so it can be a triangle, a square, a rectangle, a pentagon, a kite, right? Any shape, any shape. So a polygon with diagonals, so as long as it has diagonals, has 2 fewer diagonals as sides. meaning if it has 4 sides, it has 2 diagonals. If it has 5 sides, it has 3 diagonals, excuse me, and so on and so forth. So what we want to do is, this is a conjecture, so this is just a statement that somebody made, and we want to say, is there a counterexample to show that this is false? Okay, if we cannot come up with a counterexample, then the statement we assume is true. So let's look here. So an example here, I'm going to draw, let's start with a triangle. So here, a triangle, I drew a right triangle, but it doesn't matter. Triangle doesn't actually have any diagonals because when I try to connect any of the diagonals, it's already drawn. So triangle is not going to help us here. Okay. Now I'm going to draw a rectangle. Right? We're just going, I went 3 sides, now I'm going 4 sides. So a rectangle has 4 sides. So if this conjecture was true, it would have 2 diagonals. And so it has 2 diagonals. And so that's going along with the conjecture, right? 4 sides, 2 diagonals. Okay, so that's not a counterexample. Now let's draw a 5-sided shape. So I'm going to draw a pentagon, and it's probably going to be really poorly drawn, but we're doing our best, right? Okay, so here's a pentagon. I'm going to draw all the diagonals. So I have one here. So there's 1, there's 2, there's 3, there's 4, and there's 5. So this is a 5-sided shape, but it has 5 diagonals. And that goes against this conjecture, right? Because if this conjecture was true, a 5-sided shape would have 3 diagonals. And here I have 5. So because I have proved this conjecture true, right? Because I found something that didn't fit this conjecture, I've used a counterexample. So my counterexample is a pentagon has 5 sides and 5 diagonals. So that is a counterexample. That is proving that that conjecture is not true. Okay. Now for this, try it. I want to, you guys are going to try it on your own, but I want to explain kind of some of the words that are in here first. So the conjecture is the sum of 2 composite numbers must be a composite number. And so that's kind of a new word. So we're going to go ahead and define that first. Okay, so a composite number. So the definition of a composite number is a number, obviously, right? A number that has factors other than 1. Other than 1. Meaning it can be split up into 2 numbers, like 6 can be split up into 2 times 3. Or 9 can be split up into 3 times 3. Or 15 can be split up into 3 times 5, right? So any number that can be split up. So here, the conjecture is the sum of 2 composite numbers must be a composite number. So I want you guys to see if you can come up with a counterexample to that. And just test it out, see what happens, right? See how it goes. So go ahead and hit pause on the video, and then we are see if you can come up with something that does not work for that. So see if you add two composite numbers together, two numbers that aren't prime, do you get something prime? Because if you do, then that is a counterexample. So go ahead and try to find a counterexample, and then we'll meet back and talk about it. Okay, so hopefully we messed around with some numbers and tried and see if we could get any ideas. So you could do something like 4 plus 6, right? 4 plus 6 is 10. 10 is a composite number, so that doesn't help us. You could have done like 9 plus 6, let's just say, which is 15. That can be split up, right, into 3 and 5, so that's not helpful. But hopefully if we kept trying numbers, we found maybe this combination, 4 plus 9, right? 4 can be split into 2 and 2. 9 is 3 and 3, so they are both composite. If I add those together, I get 13. 13 is a prime number, so this actually goes against that conjecture, all right, because 13 cannot be split up by any numbers other than 1 and 13. Another possible example that you could have found, is 9 plus 8, right? So 9 is 3 and 3, 8 is 4 and 2, so two composite numbers. And if I add them together, I get 17, which is a prime number. And I cannot break that up any further. And there are other options out there, so you definitely could have found other examples on other counter examples, totally just blanked. Other counter examples, but this is just two options, okay? So if you had another counter example that you think works, as long as these two numbers are composite and this number is prime, it will be a counter example. So the last problem that we have to look at is example 5. Can I fit it all onto one? I think so. So example 5 is all about testing a conjecture. So again, if you're given something, how can you test it? How can you make sure that it's actually true? Okay, so you can either provide a counterexample to show that it's not true, or you can test all of the different options in that conjecture to see if it is true or not. So let's just look at A real quick, and then I think this will kind of make sense. So, we got a pin on. Okay, so a polygon, so a shape with 4 congruent sides is a square. So we know, obviously, right, that if I have all 90-degree angles, so 4-sided shape, and if I have 4 congruent sides, that's a square. But can we provide a counterexample? Right, so can we provide a counterexample? So can we think of a 4-sided shape where all 4 sides are the same, but it's not a square? And so what that leads into, what if my angles weren't 90? What if I shifted this into, I can draw it better, sorry, something like this, right? Where all 4 sides are the same, and I know they're the same because I drew those tick marks. All 4 sides are the same, however, I'm just gonna make that better. The angles are not 90. Because it doesn't say anywhere on here that the angles have to be 90. It just says 4 congruent sides, okay? And this shape right here is a rhombus. So 4 sides without the 90 degrees is a rhombus. So that provides a counterexample, right? So we can't say that any polygon with 4 congruent sides is a square. Can't say that because it could be a rhombus. Okay, so a rhombus just doesn't have those 90 degrees. For part B, if a number is a multiple of 9, then the sum of its digits is a multiple of 9. So this is a really interesting one because I can do 9 times 1, 9 times 2, 9 times 3, right? Any multiple of 9, and that goes on forever. We can do 9 times 17, 9 times 18, 9 times 19, and so on and so on. So there's no way that I could test every single number. Okay, so I'm going to just make a quick note of that we can't test every number. It's just impossible, right? Multiples of 9 go on to infinity. So there's no way we can test every number. So what we're going to do is we're going to pick a sample. Pick a sample size. Or just a sample is fine. So we're just going to pick a couple random numbers to multiply 9 by and then see if it works. So 9 times 12, right? 9 times 12 is 108. So this says if 9 times 12 is 108, then the sum of these three digits, 1 plus 0 plus 8, so 1 plus 0 plus 8, it should also be a multiple of 9. So 1 plus 0 plus 8 is 9. And is 9 a multiple of 9? Yes. Okay, but it's not good enough to just test one point. So let's test some other points. 9 times, I don't know, 313. You can pick any numbers you want, okay? 9 times 313 is 2817. So if I add up all those digits, 2 plus 8 plus 1 plus 7 equals, right? 2 plus 8 is 10, plus 1 is 11, plus 7 is 18. Is 18 a multiple of 9? Yes. Okay, now let's try this. 9 times 1,105. Which is 9,945. If I add up these numbers, 9 plus 9 plus 4 plus 5. 9 plus 9 is 18, right? Plus 4 is 22. Plus 5 is 27. Is 27 a multiple of 9? Yes. Okay, so I'm just picking a small sample, but I'm picking random numbers throughout this sample. So you can pick whatever numbers you want to multiply. To multiply here. Okay, so 12, 313, 1,105. We're just random numbers that we picked. You can pick anything. So since my random sample size works for that conjecture, we can go ahead and say that that conjecture is true. Okay, so for the triads, these are maybe a little bit on the tricky side, but I really do want to want you to try this. Okay, so think about it. Plug in numbers, test things out, see if you can come up with a counterexample, see if a sample of numbers works, things like that. But I would spend, a good 5 or plus minutes working through these to see if you can figure out whether or not the conjecture is true or not. When you are ready to go over it, go ahead and hit play, and I'll see you in a second. Okay, so hopefully you gave it a shot. We're going to go ahead and go through these really quickly. So we're going to test the conjecture with several more examples or find a counterexample to disprove it. So here, for every integer n, the value of n squared is positive. So we could just start picking numbers, right? Maybe we do 4. let's actually write this correctly, Miss G. Huh? How's that? Okay. So if n is 4, 4 squared is 16. That's positive, right? What if n is a negative number? Negative 2, right? Then I have negative 2 squared equals positive 4. Okay, that's also positive. So far my conjecture is working. So you have a positive number, I have a negative number. What about the integer 0, right? You test a positive number, test a negative number, then test 0. Here, n is 0. If I take 0 squared, I get 0. Is 0 a positive number? No, it's not, right? So 0 is not considered positive or negative. So this is not a positive or negative number. So 0 is actually my counterexample here, okay? Because 0 is an integer, and if I square it, I get 0. But 0 is not positive, right? I was trying to prove that if you square it, you get a positive number, and I don't in this example. So this is my counterexample. So this conjecture is not true because of my counterexample. And then the last one, B, a number is divisible by 4 if the last two digits, are divisible by 4. So let's just pick a random number, 7, 3, and then the last two digits have to be divisible by 4. So 24, right? 24 is divisible by 4. So then I'm asking myself, is this big number divisible by 4? And if I do it on my calculator, I get 1831. So that actually works, right? Because I don't get a decimal. What if I do like 184? 84 is divisible by 4. So I'm going to check in my calculator. Is that divisible by 4? And when I plug it in, I get 46. So that is divisible by 4. So far it's working, right? As long as these last two digits are divisible by 4, the whole number is divisible by 4. So let's keep going. 248. 48 is divisible by 4. So is 248 divisible by 4? Yes, it's 62. And then let's do something like crazy. 8, 4, 3, and then 1, 2. Is 12 divisible by 4? Yes. So is that whole number divisible by 4? Yes, it is. And I get 21,078. Okay. There should be a comma there. So we have tested a sample group, and it has worked every single time, right? We've tested 2 digits and 3 digits, 4 digits, 5 digits, and it would just continue on. If it was one of these were negative, it would be the same thing, just negative. So it seems to be working. So we can assume that this conjecture is true. Okay. That's actually it for 1.4. Again, reach out to me, reach out to your teachers if you need help on any of this, or if you have any questions or need help on the homework, whatever it is, we are here to help you. Please let us know. Otherwise, this video is done, and we will see you when we do 1.7. Bye.